All right, so for the first few lectures, we've learned quite a few different reactions. All of these reactions right here can be found at the end of the chapter in the overview of reactions. The upper half, though, these are all of the electrophilic aromatic substitution. These are really important versatile reactions. Today, we might get into the other class that's nucleophilic aromatic substitution reactions, and those go through a very different mechanism. In addition to that, we also have these reactions down here where we can further change the functional groups by doing reactions like reducing a nitro compound, brominating a benzylic position, or oxidizing a benzylic position. And we also saw this Clemmensen reduction. And what was the cool trick with the Clemmensen reduction? Why do we do that sometimes? It was to avoid rearrangements with an alkylation, right? With alkylation, we oftentimes ran into over-alkylation and rearrangements. The Clemmensen reduction is a nice way of controlling it. However, it uses zinc or mercury, which isn't super friendly, and it uses hydrochloric acid, so you can't have any acid-sensitive functional groups. In addition, I really like this table in the textbook where it says you can actually change some ortho-para directors to meta-directors and vice versa. So for example, if you've got a nitro group, that's a meta-director. If you reduce it to an amino group, now you've changed it to an ortho-para director. So you can actually switch the regioselectivity depending on the functional group. Same thing with a methyl group. You can oxidize that, and that changes it from ortho-para to meta. And if you've got a ketone, you can reduce that to an ortho-para director, or you can brominate toluene and make it a meta-director. So these are some useful synthetic tricks. There's two main things I want you to pay attention to anytime you're doing synthesis problems, though. And here's the first one. The first one is one that isn't talked about very heavily in your textbook. But if you have aniline and you try to nitrate it, do you think it would go ortho or para? Or both, or would it go meta? A little bit weird. The reality is it just forms goo. Tricked you. Nitrating anilines is really hard. Oftentimes what you get out of your reaction is polyaniline, which is just a oligomeric goo. It's not a very good reaction. Part of the problem is the nitrogen on here can act as a base, steal a proton, and it just goes all haywire very, very quickly. So try to avoid doing that reaction. Number two is this reaction where, let's say you've got a nitro group on there, and you tried to do an acylation. Oops, sorry, I forgot my L. This one won't work. Why not? Anybody remember? We've got a really strong electron withdrawing group. We said with Friedel-Crafts alkylations or acylations, you can't have a strong electron withdrawing group. So anytime you're doing synthesis problems, there's two things. Try to avoid installing electron withdrawing groups until last. If possible. Sometimes it's not possible. To avoid limiting yourself, right? If you install that nitro group, you can't do alkylations, you can't do acylations very easily. So maybe install that nitro group later on in your reaction sequence. Does that make sense? And then number two is pay attention to reaction order. It's pretty tricky, especially with a lot of these aromatic substitution reactions. So let's do a practice problem first, and I'll show you guys a little bit of this challenge. So propose a synthesis from benzene. And I'll give you the target molecule. The target molecule looks like this. It's got a ketone on it. It's got a nitro group over here. And it's got a bromine over here. So let's try to figure out a way to make this starting from benzene. And like I've said all year long, working backwards is your best route. And try to see all the different routes and try to rule out the ones you don't think are likely to work. So I'll give you guys a minute to work on this, but try to work backwards. All right, you guys want to try this as a class now? All right, there's 3 options, right? So I'm just going to arbitrarily pick one group to install. So for example, I'll say, all right, maybe the intermediate before the final product was missing this nitro group. So I'll draw that in. And I would say, all right, that would mean the ketone must have been on there originally, and the bromine must have been on there originally. And what are the reagents we need to install a nitro group? HNO3 and H2SO4. Will this reaction work well?
Yeah. There's already 2 deactivated.
It might work well. So I'd say that would be okay. So let's do this one and say, all right, this bromine we know is an ortho-para director. It's kind of weird. It's a weak deactivator, but it's still an ortho-para director. And then this group over here, what is it going to be? Meta director. So again, it's going to point to one of those carbons. So I'd say immediately we can check in on this one and say, yeah, maybe we can install that nitro group last. Okay, let's just do the other options though. So maybe instead of the nitro group, let's try the bromine and say, all right, if we focus on this bromine and we say, all right, we want to install this one in our last step, let's check. And then we could say, all right, that means the ketone could have been on there originally and the nitro group could have been on there originally. What reagents do we need to install a bromine? Yeah, Br2 and iron tribromide. All right, same thing. We can circle this and we can say, all right, that's a meta director. Only available meta position is right there. And then alternatively, we could say we've got a nitro group right here. That's going to be an ortho-para or meta director? Meta. So again, we can point to this carbon. Is this reaction going to work well? No, it won't give you the bromine at the correct carbon. So I would immediately go ahead and say, all right, we're going to rule that one out. And then we'll go down to our last option down here and we'd say, all right, what about this ketone? If we did this option, we would still have our nitro group on there. We would still have our bromine on there. And again, we could look at our nitro group and we would say that's a meta director. Got a meta position here and a meta position here relative to that nitro group. The bromine we know is going to be ortho or para. And students would say, well, if you think about sterics, maybe it will install at the correct position. You guys think that's the case? Why not? Anybody want to share a theory or idea? Let's take a look at the reactants we need, right? We need our acid halide and aluminum trichloride. This is a Friedel-Crafts acylation. Will this work? If we go back up to our tips and tricks, I said Friedel-Crafts acylation will not work if you've got a strong electron withdrawing group, right? So if we go through and we look at this one, we would say this really won't work very well, simply because it's got this electron withdrawing group here. Oops. So this is 2 deactivated. All right, so it looks like we're on the right track. Now what we need to do is figure out, all right, we've got this compound. Let's work backwards and try to make para-bromoacetophenone. So I'll just do this again. So continued down here. We're going to try to make parabromoacetophenone. That's our target because we need that in our last step. We've got two different ways to make this. One step would be to start out with regular acetophenone and try to make this. The other one would be to start out with bromobenzene and try to make parabromoacetophenone. All right, for the top one, again, we could say, all right, we've got this ketone right here. Is that an ortho, para, or meta director? Meta. So it would favor right there or right there. That means immediately we can cross out this route and say that's not likely the best route. Let's double check though and say, all right, the bromine right here, is this going to be ortho or para? In this case, we know we want the para one. So we might take a little bit of a hit where we do get some ortho substitution. That's fine. But at least we're getting some of our desired product. All right, the reagents we need for this final step are going to be the acid halide followed by aluminum trichloride. So this is essentially how I do my reaction planning with electrophilic aromatic substitution. Whoops. It takes a lot of work and a lot of space. Whiteboards are going to be your best friend when you're doing these practice problems. Try to work in a group if possible, because they might catch one of those mistakes that maybe you forgot about. So for example, strongly deactivated rings, people forget about that all the time. And then when you're done, just try to couple it all together. So I'll write full scheme. We know that we can go from benzene to bromobenzene. Oh, actually, I'm going to keep it just oriented the same so we're not confusing ourselves. To parabromoacetophenone. To our final product where we did that last nitration step. And it's always a good idea to double check your work and make sure that you know all of the reagents. I'm not going to include the reagents here because we've already included that in our scheme right above. Does that make sense? Takes a lot of work to get good at these. All right, let's go on to the new reactions. These new reactions are completely different than the ones we've been learning about. We've been doing electrophilic aromatic substitutions. These are all nucleophilic, and I'll show you the difference, but I'll show you an example of this reaction first. The thing with this reaction is you have a leaving group. In this case, it's usually going to be a halogen or a tosylate group. You're going to treat this with a strong nucleophile, like hydroxide, and then follow it up with an acidic workup. And when you do these reactions, you can actually swap out your leaving group with your nucleophile. So let's circle this and we'll write leaving group. And then over here we'd say nucleophile. If we think back to the last reactions that we were doing, the electrophilic aromatic substitution, the aromatic ring was the nucleophile. So it was doing the attacking. In this situation, it's actually being attacked by another nucleophile. So it's completely flipped. So let's take a look at the mechanism. And I'll just do the same starting material where we've got bromine para to a nitro group. And we have hydroxide in step one. We know hydroxide's a pretty strong nucleophile. Now the question is, which position on the aromatic ring is likely to be attacked? What do you guys think? So will it attack at the red position, the green position, the blue position, or the purple position? Why? Because BR is a good leaving group. All right. Besides that. Let's think about the electron pore sites on the aromatic ring. Where are the electron pore carbons? Yeah, the nitro group's strongly electron withdrawing, which means your ortho and para carbons are going to be electron poor, right? So we can go ahead and we can label that. So I'm going to go ahead and label my electron poor carbons, and I'm going to say, all right, electron poor carbon right here, here, and here. Those are ortho and para to our strong electron withdrawing group, and you can rationalize this by drawing all the resonance structures, right? So in this case, our strong nucleophile prefers to attack at one of those sites. In addition, it prefers to attack the site with the leaving group. So it's going to attack right there. And you can't have a Texas carbon, so we must also displace some of these electrons. And I'll just put them on this neighboring carbon. Doesn't matter if you go left or right, it just depends on how you draw your aromatic ring. And we've got this anion. This looks pretty unstable. However, I'm actually going to draw out full bonds here. It is an allowable anion. Does anybody know why? It's going to sound like a broken record. Resonance, right? So you can go ahead, and the reason that this is resonance stabilized is you can actually take this negative charge and push it all the way to that nitro group, right? We know the nitro group really wants to pull electrons towards it. So one of the major contributors for this resonance structure is one where the electrons are being completely pulled to that nitro group. And this is referred to as a Meisenheimer complex. All right, the next step is pretty straightforward. We're going to go ahead and form our product. And the way this happens is one of these electrons can actually kick down, kick over, and eject off your bromine. So essentially it's a cascading effect of electron pushing. And at this point we're almost done. However, we are going to run into a problem because chemistry is never easy. The problem is this reaction is normally done with excess hydroxide. If you've got excess hydroxide around, it can continue to do acid-base chemistry, right? Where is the most acidic proton on this molecule? Yeah, on the alcohol, right? And in this case, it's actually surprisingly acidic. Not only because it's attached to an electronegative atom, but because your final product is highly resonance stabilized. So it's very hard to stop at your final product. Instead, you form your phenoxide anion. Which is why in step 2, you end up treating this with acid in order to ensure that your final product has a proton on that oxygen. And there you go. Does that make sense? Yeah.
Why do you have a complex? I know you talked to me about sigma complex, breaking aromaticity of aromatic compound.
Mm-hmm.
Is it the same thing here?
Yes, in this case, if we look at our Meisenheimer complex, right here at that top position, we've got an sp3 hybridized carbon now, right? Which means we broke aromaticity. This is a hard reaction to perform, but I will show you the key features that allow it to occur. You are breaking aromaticity though, so this is a very uphill reaction. So let's look at the things that are required for this reaction to occur. All right, first one is it must have a strong electron withdrawing group. So a nitro group, something like that, that's very, very strong electron withdrawing group. And then number 2 is you must have a leaving group that is ortho or para to the electron withdrawing group. And like I said, this could be any leaving group. It could be something like a tosylate, it could be a halogen, anything like that would work. But it has to be ortho or para. And we know that because if we look up here, if it's ortho or para, it allows for this resonance stabilized Meisenheimer complex, where if it's meta, it doesn't allow for that. Yep. All right, so it is kind of a weird reaction. It has a lot of rules you have to follow, but if you ever see a nitro group and a leaving group, you might think about this reaction rather than our normal electrophilic aromatic substitution. All right, there's one last reaction. It's kind of similar, but a little bit different in terms of its mechanism. This is called elimination addition, and I'll show you a few different cases. So let's say I do this reaction where I have sodium hydroxide followed by an acid workup. What will happen? Nothing will happen, right? We don't have an electron withdrawing group like a nitro group ortho or para to that halogen. So nothing will happen. No reaction. All right. However, chemists are never satisfied with a no answer. And so what do you think they did to try to get this to work? So same reagents. And they were actually able to swap out that bromine for an alcohol. If a reaction doesn't work the first time, what's the easiest approach to really make it go? Crank the heat up, right? If something's not working, just blast on it. And that's what they did. They actually got this to work under incredibly high temperatures. So under room temperature, it won't occur, but if you heat the snot out of it, it will occur. The problem with this is usually the temperature is so high that if you have other functionality, you're just simply going to cook your molecule and destroy it. So it's not a very useful reaction. However, there's another reaction that's pretty similar that's more common. Oops, sorry, this is a bromine here. Where you can actually swap out a bromine for an amino group and make anilines. And to do this, you need a very, very strong nucleophile, sodium amide, and ammonia. And if you remember, the sodium amide, sodium's positive, nitrogen's negative. So that nitrogen is one heck of a good nucleophile, a lot better than oxygen. And why is that? So why is that NH2 with a negative charge more nucleophilic than hydroxide anion? Going back to first term. Electronegativity, right? So if we think about electronegativity, oxygen's very electronegative. It's okay with the negative charge, where nitrogen, a lot less electronegative. That means it's going to be very, very reactive with the negative charge. So this one actually works under moderate temperatures. And so for a long time, people were trying to figure out why this works or how it works. We knew that it wasn't going to be the nucleophilic aromatic substitution because we don't have a strong electron withdrawing group. And so what they did was a really fascinating experiment, and I forgot the chemist's name that did this. But he did it with parabromotoluene. And he knew that this reaction didn't have a strong electron withdrawing group, and so he treated it with sodium amide, the better reagent. And if we think about sodium amide, it's a really good nucleophile, but what else can it do? It's a good base, right? Oftentimes good nucleophiles are also good bases. So what's believed to occur is a deprotonation of an adjacent proton to your leaving group. So in a way, this kind of looks like an E2 reaction. You end up with a triple bond. And this is referred to as benzyne. Has that Y-N-E suffix to indicate the triple bond. So this is an elimination in the first step.
Why is it called benzyne if you have like a bond group? Should it be called polyol?
It's still a benzyne derivative. You'll refer to things as benzynes anytime they look like a benzene with a triple bond. Yeah. All right, so this is hugely reactive. It's not very happy, and why is that? Bond strain, right? We know sp hybridized carbons prefer to be 180, not angled like that. All right. And the neat thing with this was in the next step, they actually observed two different products. Both of which involve an attack from the sodium amide. So in the first one, for example, it'll attack this carbon, kick electrons over. You'll get a negative charge plus your aromatic ring. Or it can attack the top carbon and kick electrons over to the right. And in fact, both intermediates are observed for this reaction. So this is the addition step. Yep.
So why is there no nitrogen still in the molecule?
Oh, sorry, I forgot my groups. Thank you. I'm completely forgetting my NH2s. There we go. That looks better. All right, and then in the last step, we need to form our final product. And the only base around is ammonia. Or sorry, only acid around is ammonia. It's not a very good acid. However, this is a really, really strong base. So in the next step, it's going to steal electrons. Or sorry, steal a proton from ammonia to give you your final product. And there you go. So this is the full mechanism for elimination addition. And for a while it was hotly debated about whether or not this was the true mechanism. Oh, thank you. Holy cow. It's a good thing you're around. And people were arguing about the benzyne, and they said, I firmly believe that benzyne intermediates do not exist. And I'll show you one of the clever ways they actually came up with for kind of showing that it probably does exist, was they were able to make one of the theorized benzyne intermediates. I'm not going to show all of the functional groups. And they treated it with a diene. What does this look like? like a Diels-Alder reaction, right? You've got a diene here, and this could be a dienophile. And what they found was, in fact, this can do Diels-Alder chemistry. And when you do this, you can trap your benzyne intermediates. And just like we saw last term, that oxygen will act as a bridgehead. Really, the only rational way for this reaction to occur is by truly having a triple bond in that position. And so this was more evidence they used to support that benzyne intermediate mechanism. Does that make sense? It was pretty cutting edge chemistry when they did this. A lot of people even today argue about benzyne. And in fact, there is some evidence that maybe this isn't the full story. Maybe it's not a true triple bond. Maybe it's more of a diradical. And that debate is still kind of ongoing. The reality is, in most of these debates, the truth is kind of in the middle. It's not one or the other. All right. So that's the end of the reactions for this chapter. For third term, I really recommend going through the chapter's summary sheets at the end of the book. These are really good review aids. And in addition to that, what I've done is I've created a fill-in-the-blank study guide. Whoops. Come on. Where you can print these off and then just add in the reagents as needed. You can also add this into your reaction map that you made last term. It's probably getting pretty crowded at this point, so it may need to be rewritten a little bit. But use these as much as possible.